All right, welcome back, kids. And yesterday we spent some time looking at a type of motion called a vibration, and we looked at the three different types. Now we want to look at a phenomenon that is produced by vibrating objects as the energy that starts in that vibrating object starts to spread away from the vibrating object through some material. And that energy that spreads away from the vibrating object is called, you guessed it, a wave. I'm waving at you. So let's get started. All waves are produced by a vibration. That's the source of the energy. For example, sound waves. I'm speaking, my vocal cords are vibrating, that energy is being spread through the air particles around me into the microphone. So my human vocal cords are a vibration and they produce a wave that spreads that energy, and that is a sound waves. Waves transfer energy from one position to another. Most waves require a material. Another word that scientists like to use for material is a medium. So most waves require a material to travel through. For example, sound waves can travel through the air. If you've ever been maybe swimming underwater, you may have heard a noise. That was a sound wave traveling through water. Also, just like we put vibrations, just like we put vibrations into categories of transverse, longitudinal, and torsional, same thing with waves. If you've got something that's vibrating, it may produce a transverse wave. It depends on how the object is vibrating and the material that the energy spreads through. If you've got an object that's vibrating, it may produce a longitudinal wave. Depends on the material and how the object is vibrating, and similarly for torsional waves. So let me give you an example through this animation, and I'm going to put the links on the website. But here is the vibrating object. It's represented by this gray bar right here, and it's moving forward and backwards, forward and backwards. And as it moves forward, it compresses these particles, and they all bunch up. And then as it moves backwards, it makes space, and particles rush into that space, but they're spread apart. And this repeats over and over and over again, and you'll see the compressed part move forward. You'll see the spaced out part, or rarefaction, to make rarefaction. You'll see it spread out and move forward. But what you really have to be careful about is if you watch an individual particle, they've made this particle red, look what it does. Particle moves forward, particle moves back. Particle moves forward, particle moves back. If you were able to isolate any particle in the material, in the medium, that is spreading the energy of the original vibrating particles, they actually repeat what the vibrating object did. The vibrating object here, the gray, moves forward and backwards, moves forward and backwards. All the other particles, they've isolated a red one here, a red one here, a red one with an arrow here, a red one with an arrow here. They just move forward and backward, repeating the vibration of the original vibrating object. What moves forward is the spreading of the energy, and that's what we call the wave. Look, this compression is moving forward. That's part of the wave. All right, moves forward. This area where we have rarefaction right here, it's moving forward. The compressions move forward, the rarefactions move forward, the waves move forward. But the individual particles only repeat what the vibrating object did. A very important concept when studying waves. Similarly, for transverse waves, you've got something moving up and down, right? Moving up and down, and look at what all the particles are doing. If you were to isolate any particle, pick any particle, let's pick this one right here, up and down, up and down, up and down, just like the original vibration, just like the original vibration. This particle right here is not moving forward. None of the particles are moving forward, but look, up, and the up part moves forward. See? That part upward moves forward, and the downward part moves forward. So the part that's up moves forward. It's called a crest. The part that's down moves forward. It's a crest. The wave energy moves forward, not the particles themselves. The particles themselves are just a material, a medium for which the wave to spread through. They don't move forward. It would be like if we were back in the classroom and I was speaking to you, the particles that were in my mouth would have to move forward out into the classroom for you to hear me. That's not what happens. The particles in my mouth hit the next particles just outside my mouth, and then they hit the next one, and the next one, kind of like a domino effect, until the particles near you and near your ear start the vibration. Very important you realize that. Now here's another simulation. I've put the link on the website to help you understand this. The blue object is the vibrating object, and it's going to vibrate two materials. It's going to vibrate two materials at the same time. So it's connected here and it's connected here. So it's vibrating. You can picture this to be kind of like a slinky. It's a wonderful toy for a girl or a boy, slinky, a slinky. So right here, and it's also maybe attached to a string or something, or a spring, so it's attached to two things, and because of the materials are different, you're going to get different types of waves. Watch. There you have it. A transverse wave is created here. A longitudinal wave is created here. I'm going to stop it for a second. But here would be an area of rarefaction of it, where the particles are very far apart. It moves forward. Here would be an area of compression. It moves forward. So let's take a moment to watch the compression, the compression and the rarefaction move forward, while each individual link stays there. It doesn't move forward. Okay? Very important you see that the individual particles stay there while the energy from the vibrating object, the wave, moves forward. This is what we call a transverse wave. Let's stop it here for a second. This part that's up top right here, it is known as a crest of a transverse wave. This part over here is known as the trough of a transverse wave. There you have it. Now I'm going to stop this, reset it. Now one of the things that we can change is how far the vibrating object actually moves, and therefore the size of the wave, how much it's compressed by, how big the crests are depending on the wave. So it was 3, let's put in a 5 now, and you'll notice it's going to be different. See how um, the crests are larger, the troughs are larger, and the area of compression is quite magnified now. It's very compressed, and the area of expansion or rarefaction is even more expanded, more rarefied. Let's let it go because I changed the amplitude. All right, so let's stop that and let's go to an amplitude of 0.5. Let's see what that does, and we'll reset and go. Very small, see? The compressions and rarefactions are hardly noticeable there, but they're there. And look how tiny the crests and the troughs are, right? Here's a tiny crest, tiny trough because we changed the amplitude. So depending on the amplitude of the original vibrating object, it has an influence on the amplitude, be it seen as a crest or a trough, or be it seen as a compression or rarefaction. It has an influence on that. The amplitude of the vibrating object influences the amplitude of the wave that is created as that original energy from the vibrating object spreads away from it. So now this is running as it was when we started, amplitude 3, and then frequency. Remember we learned about frequency yesterday? Frequency tells us how many cycles per second do we get. All right, and remember what a cycle is. It's 4 amplitudes. So let's start our count here. 1, 2, 3, 4, back where it started. 1, 2, 3, 4, back where it started. And you can see the amplitude repeated in the waves. Watch. Go up is 1 amplitude. Come back down to 0, 2 amplitudes. Go back down further, 3 amplitudes. Come back to rest position, 4 amplitudes. So up to 0, all right? And then uh, coming back down, then going the other direction and coming back up. There's 2 amplitudes in each trough, 2 amplitudes in each crest. So you got to realize that as a vibrating object goes through its frequency and period, the wave also goes through its frequency and period. So please remember there's that connection. Let's try to demonstrate this by changing the frequency here. Here the frequency was 0.5. So let's make it 1. And we'll see what happens, right? I don't know. I do know, but I'm pretending. Okay. The waves are become much more compact here. The the crests are closer together to each other. The troughs are closer together to each other. You get more waves in a certain amount of time. So that's 1 for a frequency. Let's change it to 0.1. Let's see what that does. Much slower vibration. Look how long it takes to go through a crest or a trough. You can't even see a complete one there. All right, much slower vibration. So some of the things that we can change for a wave is amplitude and frequency. And you can play around with this simulation to help you understand these things. Playing around with it is the best way to learn. Okay, and I'm going to leave all the links for you. Here's another great simulation. I really like this simulation to help us understand uh, waves. So let's let it run through. There you have it. The vibrating object transfers its energy through a material, and the energy moves forward. All right. So let's re let's restart. So it's back to 0, and we're gonna move through here bit by bit. So watch. 1, 2, 3, 4, 5, 6, 7, 8. And now the object has gone through 1 amplitude of vibration, and it has created half of a crest. Let's keep going. Now we've gone through, went up, came all the way back down, so it's gone through its second amplitude, and here's the second amplitude. It has completed the crest. So now this vibrating object, represented here by the green, it's gone through its third amplitude, and it has created the first half of the trough. Let's keep going. Okay, I might overshot by a little bit, but you get the point. Now it's gone through the fourth amplitude of its vibration. All right, it's created the second part of the trough. So now we've gone through 4 amplitudes. That's one cycle. That is known as one complete wave. A complete wave has 4 amplitudes. A complete wave has a crest and a trough. The time it would take for this to occur is known as the period of the wave. We talked about period yesterday when we were talking about vibrations. So just like this vibrating object went through its period, this wave went through its period. And this is summarized here in the note. We kind of summarized it in the note that as a vibrating object goes through 1, 2, 3, 4 amplitudes, it creates a complete wave with a crest and a trough. And the distance from the uh, start of the wave, the original vibration, the distance from here all the way through the complete wave to here, that entire distance, that entire length is known as the length of the wave. But they don't call it length of the wave. They give it a very special name. They call it wavelength. Wavelength. And a complete wave is 4 amplitudes. The vibration and the wave have gone through one cycle, and we call that one wave, one complete wave. Now that wavelength, you would think, oh, what's a good symbol for wavelength? L. Well, they don't use L. They use the Greek letter L, which is lambda. It looks like this. Okay, so I've drawn it larger here. A complete wave is a crest. There's the amplitude of the crest. A complete wave also includes a trough. There's the amplitude of the trough. It's negative A, and this would be positive A, measured from the rest axis. And a complete wave here from the beginning to the end is the Greek letter for L, lambda, known as wavelength. 4 complete waves. All right? Now, sometimes you don't have a complete wave. Sometimes you only have 2 amplitudes, which is half a cycle or half a wave. So it's not called a complete wave. It's called a pulse. So it just goes up and down. Let's have a look at that. So we're back to this simulation. I've set it up for a pulse, 2 amplitudes, up, down. Ready? Here we go. Up, down. And the up, down is repeated by every particle here. This object went up, down. Now watch this object. Up, down, up, down. They all repeat the same thing. That's what a wave, or in this case a pulse, does. It repeats the motion of the vibrating object. If the vibrating object goes up, down, this particle up, down. Every particle goes up, down. This object went back to just sitting there being at rest. And then once the pulse goes through, that's what they do. It repeats what the vibrating object does as the vibrating object's energy spreads forward in a wave-like fashion. And that's what I've drawn here. This is a pulse. Up, down. That's it. And it moves forward with a certain speed, V. All right, a certain speed, V, is how quickly that pulse moves forward. You can also write it down here, V, right? Probably shouldn't put the vector. Let's get rid of the vector. Speed, how quickly does that energy move forward in the form of a wave? Now, the next thing we want to talk about is how waves reflect off things. And we're going to go back to the simulation to help us understand that. So we want the wave to bounce off something. It's easier to visualize if we just use a pulse because there's only 2 amplitudes for us to keep track of. But it's the same thing for a wave, but we're going to use a pulse to help us visualize. So here we go. Here's the pulse. Off it goes, and boom, it's off to visit Peter Pan and Never Never Land. All right, but now we want to change it. Now we want to put a material there that is going to interact with the pulse, the wave, as it approaches it. The first thing we're going to hook up here is we've got this spring, and it's hooked up to a ring, and the ring can move easily up and down the rod. Let's see what happens. Aha! The pulse is reflected back. All right? The pulse is reflected back. Let's watch that one more time. Here comes the pulse. It interacts with this object that creates a vibration. And you notice the pulse was a crest and it reflected back as a crest. Let me show you that again. Okay, crest. It's above the rest axis. Reflection occurs. It's still a crest above the rest axis. We call this open, free, or loose end reflection. And if a crest is produced, is sent to the end, a crest will be reflected from the end. Now, let's try another type of end. We clamp it down now. All right, we're going to clamp it down. We're going to produce a crest. Here's our pulse. Do, 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 moving towards the end. And bingo, bango, it has now been reflected as a trough. This is called a fixed or closed end reflection. Let's see it one more time. When a crest approaches a fixed or a closed end reflection, it reflects back as a trough. It reverses it. So we need to talk about that. And that's what I've written down here. You have a crest come in to a fixed or closed end. Bingo, bango, it hits, bang. It reflects back as a trough. We call that inversion. If it's a free or open end, as you saw, the crest comes in, boom, interacts with the free or open end, and comes back as a crest. We say there is no inversion or the reflection is upright. That's the other thing we're talking about. And the last thing we want to talk about is how fast the wave moves, the speed of the wave. Watch. Okay. So it moves forward with a certain speed there. Now what I'm going to do is I'm going to change the tension in the spring. Look, the tension is now half as much. Watch this. Moves more slowly. So the tension in a spring affects how quickly a pulse or a wave, works same for a wave, moves forward. Let's have really low tension. Let's see what happens. The pulse moves very slowly. It is eventually going to get there. I think you get the point. Anyway, tension really has a large effect on this. So, I hope these simulations help. You can play around with them. Maybe, I don't know, you want to have like a Google Hangout or a Skype or a Zoom meeting, or I don't know how you kids communicate, tic-tac-toe, Slapchat, whatever you guys want to use, and maybe discuss these little simulations, because I can't do it in real life. It really saddens me, but we're going to do the best we can. I have great confidence in all of you that you can come through, just like generations before us that had hard times. They were able to come through. We're going to be okay. So I'm going to give you some reading to do. I'm going to give you some questions to do. If you need any help, I'm here to help you. Please remember that. I'm on your side. You guys take care. Bye-bye.